Welcome, everyone. Okay, let's dive right into this. If you're aiming for true clinical mastery and you're preparing to absolutely crush your OCAPs and written boards, you are in exactly the right place. Today, we're taking abstract physics and transforming it into long-term clinical intuition. We're going to master this phenomenal mental model called the error lens concept. This isn't just about memorizing some divergence equations. It's about fundamentally understanding what's actually happening inside your patient's eye so you can diagnose, treat, and explain refractive errors with complete and total confidence. Here is our roadmap for today's masterclass. Number 1, defining the error lens. 2, the myopic plus lens. 3, the hyperopic minus lens. 4, the Galilean telescope analogy. 5, shifting primary focal points. And 6, top OCAP pearls. Mastering these 6 steps will build a powerful framework you'll use in clinic every single day.
Section 1, defining the error lens. We really need a shift in our mental models here. I want you to stop thinking about refractive errors just in terms of an eye being, too long or too short. Let's reframe this as a biological pathology. So what exactly is the error lens? Well, it's an incredibly powerful optical mental model. Instead of relying on really complex formulas, we're going to conceptualize a refractive error as if an extraneous, completely unneeded lens has been physically built directly into the eye itself. Why do we do this? Because this imaginary error lens is exactly what keeps parallel rays of light from falling precisely on the retina. By identifying the specific type of unneeded lens sitting in our patient's eye, the treatment algorithm becomes incredibly intuitive. Moving right along to Section 2, the myopic plus lens. Excess converging power. Let's look at the pathophysiology of the myopic eye and see how perfectly this concept explains our nearsighted patients. Picture this. When parallel rays of light from infinity, meaning a vergence of 0, enter your myopic patient's eye while they're sitting in the exam chair, they converge way too early. They focus completely in front of the retina. Why is that happening? Because the myopic eye has too much converging power for its physical length. So, applying our mental model, the eye is acting exactly as if it contains an extra plus lens. It's this extraneous, built-in plus lens that causes the excess convergence that completely characterizes the myopic refractive error. Section 3, the hyperopic minus lens. Excess diverging power. Now let's transition over to the exact opposite clinical presentation. How does this same model apply to our far-sighted patients? In the hyperopic eye, parallel rays from infinity just don't converge enough to hit the retina. Theoretically, they'd focus way behind it. So the eye has too little converging power. But, and here's the really critical shift in your clinical thinking, we can also describe this as having excess diverging power. Therefore, the eye's acting exactly as if it contains an extra minus lens. This unneeded, built-in minus lens causes the excess divergence that perfectly defines the hyperopic refractive error. Let's juxtapose these two clinical entities side by side to really solidify your pattern recognition here. Myopia means excess converging power, which equals an extra built-in plus lens. Hyperopia means excess diverging power, which equals an extra built-in minus lens. I want you to literally lock this visual into your memory right now, because this pathophysiological foundation dictates absolutely everything we do next. All right, time for a little active recall. Imagine we're on the clinic floor and I'm pimping you on this concept. If your myopic patient has an eye acting like it has a +4 diopter error lens, what exact corrective lens power do you need to write a prescription for to neutralize it? Think about it for a second. How exactly do we treat that excess convergence? The answer is -4. So the crucial takeaway point here is that the minus lens perfectly counteracts the excess convergence provided by that plus error lens. You just neutralized the pathology. And this brings us to a beautiful, incredibly simple treatment algorithm. To offset the error lens that's keeping parallel rays off the retina, the corrective lens must be of equal but opposite power. It's really that simple. A +4 error lens needs a -4 corrective lens. A -2 error lens needs a +2 corrective lens. Now here is your clinical caveat. This rule holds true except for whatever minor adjustment you might need to make to account for vertex distance, which we'll actually touch on a little bit later. Section 4, the Galilean telescope analogy, a classic board concept. Now, I need you to pay very close attention here because we are entering a classic board trap. When a patient puts on spectacles, they're now essentially looking through 2 lenses in a sequence, right? They have the corrective spectacle lens sitting in front of their eye and that invisible error lens sitting inside their eye. So can you think of a common optical device that's composed of a plus lens and a minus lens? A Galilean telescope.
A classic terrestrial Galilean telescope is composed of a low plus objective lens in the front and a high minus eyepiece lens in the back. Now, think about our spectacle-corrected patients. They are also looking through a combination of a plus lens and a minus lens. The only real difference is the specific order in which these lenses are placed in front of and inside the eye. And this brilliantly illustrates our next major OCAP pearl. Why does this matter clinically? Well, it perfectly explains the image magnification and minification effects of refractive correction. Think about it. A spectacle-corrected hyperope has a plus spectacle lens in front and a minus error lens inside, plus in front of minus. They're literally looking through a Galilean telescope, so their image is naturally magnified. Conversely, a myope has a minus spectacle lens in front and a plus error lens inside, minus in front of plus. They're looking through a Galilean telescope backwards, so their image is minified. It makes total sense when you break it down like that.
Section 5. Shifting primary focal points. Let's see how this builds our understanding of foundational optics. Anatomy meets optics. You've likely seen those textbook diagrams where the primary focal points of myopic, emmetropic, and hyperopic eyes are all placed at different distances from the eye. But why?
The error lens concept provides a flawless biological explanation for this. Compared to the normal emmetropic eye, the myopic eye has excess convergence because of that extra plus lens, right? Therefore, the primary focal point of the myopic eye must be positioned physically closer to the eye in order to provide the extra divergence needed to offset that plus error lens. On the flip side, the minus error lens of the hyperopic eye gives it less converging power, so it actually needs less offsetting divergence. As a result, its primary focal point is located much further away. Anatomy and optics, perfectly linked. And we've reached section 6, Top OCAP Pearls, a rapid-fire review. This is where we synthesize absolutely everything into one coherent framework to lock in your clinical mastery for the written boards and the wards. Okay, here is your ultimate rapid-fire summary. Number 1, myopia acts as an extra plus error lens, causing excess convergence. Number 2, hyperopia acts as an extra minus error lens, causing excess divergence. Number 3, treatment always requires a lens of equal but opposite power to neutralize the pathology. Number 4, a hyperope with spectacles is looking through a plus then minus sequence, a Galilean telescope, so their world is magnified. And number 5, a myope with spectacles is looking through a minus then plus sequence, a backwards telescope, so their world is minified. I want to leave you with a final, somewhat provocative thought to prime you for your next rotation. We mentioned a bit earlier that the corrective power is equal and opposite to the error lens, except for vertex distance. So I'm going to ask you this advanced OCAP-style question. If you move a corrective plus lens further away from the cornea, how exactly does that change the required prescription power for your hyperopic patient? Think about the actual vergence of light as it travels through space. Chew on that, discuss it with your attendings, and we'll break it down together in our next explainer. Keep studying hard, and I will see you all next time.